Now let me write the complete wave function which contains the time part also. This is my space part, root over 2 by a sine n pi x by a, and this is the time part. Uh, in my previous section, I have already shown that time part is e to the power minus I e t, and for infinite square wave potential, E comes out to be n square pi square h cross square by twice m a square, which we have already derived. So just putting the time part into the wave function, I get equation 15. So my general solution, including both space and time part, this is a complete solution, is like this. I will tell a few words about the probability, or the, you may call this coefficients, what are the significance of these coefficients, etc. So this is my space part. Space part contains different components of psi n, psi 1, psi 2, psi 3, etc. with different weightage C1, C2, C3, etc. Space part is this one, and my coefficient, we have already derived this. The coefficient come out to be, if I want to calculate this coefficient, the formula is this one, the space part and the wave function or any arbitrary function fx. This is my fx here in equation 18. Now what is the significance of these coefficients? If I make these coefficients mod square, these coefficients could be complex. It could be numbers actually. So numbers can be both real and complex. So we need to take the chances of getting complex coefficients. So I have written mod here. Loosely I can say that Cn square gives me the probability of finding a particle in a particular state psi n with an energy value En. Actually what Cn tells us is how much amount of psi n is present in the capital psi. That is, if I look into this equation, this Cn will tell me how much psi n is contributing to give this capital psi, which means if I want to write for psi 1, then the coefficient is C1. C1 will tell me what is the percentage of psi 1 that makes this psi complete. If psi 1 is 50%, then in this complete set of the wave function, 50% contribution comes from psi 1 alone. And if I write C2 psi 2, and if C2 comes out to be 25%, then it tells me that 50% comes from psi 1, 25% comes out from psi 2, and if C3 is say 13%, then it's 50% from psi 1, 25% from psi 2, and 13% from psi 3. And if there is another contribution C4, which is 12%, so I get 50 plus 25, that is 75, 13 plus 12, which is 75. So equating all these coefficients, I will get 100% contributions from different wave functions, psi 1, psi 2, psi 3, psi 4, etc. But in laboratory, what we get? In laboratory, we are going to measure, suppose, the energy. Then what is the significance of this Cn square? What is the practical purpose of getting Cn square then? Then the coefficients will tell me that if I make a measurement, like if I want to measure the energy, then Cn square will tell me the probability that I could get a specific energy value En. Now this is proof of Cn mod square equal to 1. I am using the normality condition of the wave function. This is just by definition. It is my time part. But if we want to write time t equal to 0, if I want to write the time functions, the wave function at time t equal to 0, that is initially. So this t becomes 0. So there is no time contribution, we get only the space contribution. So it makes sense of writing it as psi x. And why I am writing it as mod square? Because in infinite square well, I have already seen that the wave function does not contain any complex part. So from this equation I can easily write this equation, and I have to make m equal to 1, otherwise this will become 0. So m equal to n gives me 1 for this Kronecker delta, and left hand side of this equation becomes psi x mod square integration over the entire space. For infinite square well, the space is restricted between 0 to a, where a is the length of the box. So this is my condition. So using the expression of capital psi, which is actually superposition of all these small psi n components, I can write this integration. This is psi into psi, capital psi into capital psi. So I can write like this. Now why I have written it as star, though psi n contains no complex part, but Cn, Cm, these coefficients could be complex, as I have said. So this could be complex, so taking that option, taking that possibility into account, I am writing it as star. So there must be an integration sign, sorry. So summation signs and coefficients are taking out of the integration sign. I am left only with the space part of the wave function, the small psi n and small psi m. And using or exploiting rather the normality condition of the wave function, I can write this again as delta mn. Here delta mn should give me 1, so I need to put n equal to m, which will give me either Cm square or Cn square, whatever you like. I have written it as Cn square, but this is also equal to 1. This is also equal to 1, recalling this equation. So my Cm square or Cn square, that is the coefficient mod square, should be equal to 1. This is the proof. Equation 19 is there. Now let me find out the expectation value. Again I will use the normalization condition of the wave function. This is expectation value or average value of the Hamiltonian, which contains the energy term. So by definition of the expectation value, I can write it as psi star h psi x dx, and psi is this one. So writing or substituting the expression for psi, capital Psi, here in this integration, I can find out the expectation value of h. So I am hearing writing or substituting for capital Psi. These coefficients can be taken outside of the integration. I am left with psi m star h psi n dx, and I know that when h Hamiltonian operator operating on psi n, a particular state, that will give me energy value En. So using this equation, I can write h psi n equal to En psi n. Again En is a constant, so I can take it outside of the integration. I am left with inside the integration only the wave function. Now again I will be using the normalization property of the wave function itself. So I need to write for this portion of the wave function as delta mn. So if I write delta mn, again from the property of Kronecker delta, I need to stick with only one notation. So I am writing it as n. So this is the summation goes over only on n. Coefficient square will give me Cn mod square En, and I know that I have just proved it rather. Summation of n equal to 1 to infinity Cn square equal to 1. So expectation value of H is En, which I actually wanted. But what this equation tells me, this equation 20, it has a special significance. It has a physics in it. It tells me about the probability of getting a particular energy value En after measurement in the laboratory, and this energy value En is independent of time. As we can see from this equation, there is no time factor here. If energy value En is independent of time, I can tell this as conservation of energy. So this is the manifestation of conservation of energy in quantum mechanics. We have learned conservation of energy in classical physics, classical mechanics. Now this is equation 20 tells me about the conservation of energy in quantum mechanics, which means the energy value En are independent of time.